recording. The what we're discussing here in office hours, October 10th, 2021, is the hybridization and how that affects directionality of an equilibrium and stability of, well, how it affects stability of charge and therefore directionality of an equilibrium. So the overall idea here is that you need to realize that this is going to be SP3 and this one is going to be an SP. Everything's on carbon. There's no major inductive effects or anything. But even if there were, this would still be a humongous thing because hybridization would be really, really important, especially SP versus everything else. And that's because that negative charge is held a lot closer to the nucleus because an SP orbital has a lot more S character than P. P is further, S is closer. So your negative is closer to all the positives. But you need to be careful when you're drawing these because you need to know that that is in an SP orbital, because you can have examples like let me draw it. I'm trying to think of a good counterexample. And you can look at these two and think, okay, well, if I draw this, and I go, well, this atom here is SP, and this atom here is SP2. And I go, well, SP is better than SP2. So yeah, there's a CF3 group that's a little, well, maybe I drew the CF3 group a little bit close. You might go, hey, the induction effects here. But hybridization is really, really important. I'm going, okay, this carbon here is SP2. SP is closer to the nucleus than SP2, so this guy is going to be more stable. What mistake have I made with that logic? Okay, let me rephrase that. What orbital are those lone pairs in on the carbon?
The P.
Yeah, they're in a P, right? So it's irrelevant that this is an SP or an SP2 atom. They're in P orbitals. They're not in SP or SP2 atom orbitals. Up here, it was in an SP orbital. But here, they're equally in P orbitals. And it's really easy to get to think, oh, the hybridization thing, SP is really good. I'm going to look for that. And then you see something, you go, hey, the atom's SP. But then you forget that the electrons are not in the SP orbital. They're in the P orbital. And so they're in P orbitals on both cases. So hybridization doesn't matter. And then what it comes down to here is induction. This guy's got a CF3 group. This guy doesn't. So guy on the right wins. Just be careful with that hybridization thing. It matters. And we're good. Why? You're like, okay, why does it matter that much? Why are you even bothering teaching it and confusing things and adding it? It's because we're going to be talking about the chemistry of these kinds of things later on in the course. And it only makes sense why that C- is particularly stable because of the hybridization. And I might as well introduce it now. I've gone back and so previous years I used to introduce at the beginning, then I stopped because I thought it's too confusing. Then this year I tried to introduce at the beginning again, and we'll see how it goes. Yeah. Melitza, I saw you unmuted. Can't hear you if you are talking. Well, I'll happily move on to, I don't know if you have a follow-up to that. I think that was Olivia, right? I think, but if not, then I'm happy to move on to something else. Yeah, more stable. This one's more stable. This one's more stable. And it's because of induction here. And it's because of hybridization here. Because the hybridization is a tie on the bottom one, they're both p. The electrons are in a p orbital. Normally the hybridization only really matters. It almost only, keep your eyes out for triple bonds. It's only really with SPs where you really see it being a major issue.
Yeah, I was just about to ask, how do you know when to look for the hybridization to to distinguish between the two, or just induction? But I guess you just answered that.
Yeah, so you can always check the hybridization. It really matters. It's just almost never going to be an issue. A lot of these questions I'm asking, I'm drawing with resonance structures, so the electrons are almost always in a p orbital. Because you'll note there's no resonance structures I can draw with this where I use that negative charge. I can't do anything with that negative charge. I can draw resonance structures by breaking a triple bond, but then I'm kind of creating more charges.
Okay.
Yeah. Like it's always important. It's just almost never relevant. Like you'll look and go, yeah, it's in a p orbital, done. And again, if the electrons are in a p orbital in any one of the resonance structures, they've got the charge has got to be in a p orbital in all the resonance structures because they're resonance structures. So it needs to be in a p orbital. Otherwise, they wouldn't be resonance. Yeah, okay. Go ahead, Alyssa. Oh, sorry, Melitza. So how did I know it was a p orbital on the bottom ones? Because I just drew resonance. And this negative charge came from one of these bonds. And remember, I'm not allowed rehybridizing in resonance. I'm not allowed changing shape. I'm not allowed changing anything. All I'm allowed doing is moving electrons around. And what a double bond means is two p orbitals are interacting. Each one has one electron. So if the resonance structure derived from that, what I did was I moved an electron. I don't have my camera on. Like two p orbitals are interacting. That's what a double bond is. And so if I have a negative charge that arose from a resonance structure with a double bond, what I did was I took one electron from one of the p orbitals, moved into the other one. Now one p orbital has two electrons. But I'm not allowed, making that an sp3 orbital or an sp2 orbital or an sp orbital. It's resonance, so I'm not allowed rehybridizing. The electrons are just moving around the p orbitals. And up there, I knew it was in an sp orbital because this carbon has a negative charge on it, which means if I count the electrons, it has to have a lone pair. It's already using two p orbitals. And it's only got one sigma bond, like one hybridized sigma bond. And you can't have that. You need to have two. Like if you're going to mix an s and a p, you get two orbitals out. You can't get one orbital. So the other one needs to be sp. Like you can only be sp, sp2 or sp3. There's no sort of s with three p's for a carbon. That's not a thing. Though now I'm trying to figure out why it's not a thing. It would be a quadruple bond. And I think I've seen that in a few theoretical papers, but never in reality, and not for carbon. Okay, sorry, yeah, okay. Alyssa, sorry, I overtalked you there.
Hi, sir. Okay, I got two of the questions on the assignment wrong that were the Newman projections, and I made the whole like molecule, and I was kind of playing around with it, and I don't know what I did, but the one question I will just send a picture of it.
Yeah, if you want, or I don't know if you want to share your screen.
Sure.
I will stop sharing my screen, and then you can share yours.
Do I click?
It's next to the leave button. There's like an arrow up button, and that
Oh,
shares your screen. It gives you an option of what you want to share. If you want to share an app or the entire screen, and if you have multiple screens, which one?
I'll just share that one. Can you share? Can you see it?
Not yet, but probably in a second. I just see your initials. There I go. Okay, I see your screen. Yeah.
Okay. Okay. So yeah, I was just confused about this one, since I know I don't have my model kit like right with me, but I was just confused because the C2H5 and the other C2H5, like how are those next to each other?
So scroll back up to that.
Oh, the question?
So yeah, let's see the whole thing. Okay, they're not. Well, they actually are. So if you're looking straight down that eye, okay?
Mm-hmm.
What you can do by this is by elimination. We've actually rotated it a bit. So what you would do is you would draw the Newman projection you see. B, C, and D all have one of those stereo centers is wrong. It's backwards. You're trying to grab something with your left hand, but it's in your right.
Right.
And so A does have the right thing, but it's been rotated. Now we didn't say which Newman. I'm glad you interpreted it as Newman projection. Which projection describes this conformation best? It says the compound. So the compound can rotate, and you can rotate between its bonds.
Yeah.
And so with A, that's what we're seeing. I'm just going to quickly sketch the question, and we can. What am I writing on the back of? Oh, that's official paperwork. I shouldn't write on it. Okay. Yes. And A is.
Because right away I'm like, oh, okay, well, it's definitely not A or C.
Because they look next to each other or something. Gotcha. Yeah. Okay, so how about we, I'm going to just share my screen now.
Okay, yeah, sure.
So sketch out the answer.
Okay, I'm going to stop sharing.
Okay, there we go.
Let me just grab my model kit. I will be right back.
Okay, I'll start drawing and you go grab your model kit. So if we're looking down that bond, what you should see is you just draw your circle. On the back carbon, up and away is the ethyl group. In your right hand is the bromide. In your left hand is the hydrogen. And if you need to sketch that in, sketch it in. It never hurts. So hopefully anyone who's looking at this goes, yeah, that makes sense. Anyone have trouble seeing that? Well, no, I shouldn't say trouble. Anyone can't. A lot of you might have trouble. But just put yourself, pretend you are the page, and you reach out with your right hand, and the bromine is going into the page. And so if your eye is there, you'd be grabbing the bromine, and your left hand would be grabbing the hydrogen.
Okay, I am back. I'm sorry.
Yeah, listen, no problem. I'm just checking to make sure everyone has unfolded it, the back carbon the way I just unfolded it. Can you see how I got to just the back carbon there from what I saw on the page?
I'm so sorry. I'm just trying to make the
Okay.
model.
Okay, I'll leave you to do that.
So if someone else has a question before, then go
Okay,
for
so maybe what I'll do is I'll come back to Alyssa's question while she's making her model.
it. Okay.
And does somebody else have a question? Go ahead, Guntas.
Hi, Dr. Tran. Would you mind if I share my screen? I have a specific question from one of the assignments.
Yeah, go ahead.
Okay.
Happy.
Can you see my screen or?
See your screen, I see us.
Okay, all right. So I had this question on one of your assignments, and it's asked to draw both chairs. I'm just wondering, why did you draw the lone pairs on the axials all the times and the methyl groups on the equatorial all the time?
Okay. What's bigger? A lone pair or an
methyl
atom?
group?
Yeah, I think I would accept an argument. I think it's true that a lone pair actually might be slightly larger. No, it's not. I was thinking it's slightly larger than the hydrogen, but it's not. Because they are slightly closer into the atom than a hydrogen bond, but anything else is bigger than a lone pair. So what you're pointing out and going like, okay, well, this is a little weird because you're saying all the axial should become equatorial and all the equatorial should become axial when you flip chairs. And I completely agree with you. You're absolutely right. Think about, and that's because atoms suck at tunneling. So quantum tunneling, because they're big. All atoms are big. Electrons quantum tunnel all the freaking time. And that's why they're so irritating, because they're in multiple places almost at once. And they don't need to necessarily be at those places in between. Like if we think about, if you just sit back and think about the p orbital for a second, just imagine the shape of the p orbital. We say that, hey, there's electron density above and below, but right at the atom, there's no electron density possibility. But the electrons can move between the lobes. They don't pass, it's not like they transiently pass through that middle point. There's 0% chance they're there. It's not like very, very low approaching zero, it's 0. So the electron is tunneling between the two lobes, if you're thinking of it as a particle. It's not passing between intermediate space.
So you always place the lone pairs.
Yeah. So
axially?
lone pairs, exactly, because they're electrons, they can tunnel and they can invert. So nitrogen is not configurationally stable with that lone pair. That lone pair can flip to the up and down position really, really fast.
Okay.
And so it's always going to arrange itself. So, and as I note down there in the assignment thing, it can always flip. Now it actually, it doesn't affect, and it doesn't affect the answer either way. And I don't think I would actually ask a question on an exam with the nitrogen.
Okay.
No, it's not. I don't think I would not ask a question like this on an exam with the nitrogen. But you're going to see a lot of examples out there with nitrogens doing this kind of thing because, unfortunately, there's a lot of 6-member rings with nitrogen in them. It's a dominant type of moiety out there in chemistry, so you're going to run into it. So might as well see it. But it doesn't change the answer because I also didn't draw any stereochemistry for that, right? I just wrote NCH3. I didn't say what the stereochemistry was there. And the reason I didn't say what the stereochemistry was there is because it's either, because the nitrogen can flip. And that's always true with nitrogen. The only way it's not true is if the nitrogen was quaternized. So the nitrogen had 4 sigma bonds on it, it was positively charged. Then, of course, now you have atoms attached, and now it's kind of like the carbon case, so you can't tunnel.
Okay, all right. Thank you so much.
Yeah, no, it's a great question, and I hope you got the rest of it right. It was just that, and so that's good.
Yeah.
And that's why I put the little comment down there, because it's not something you necessarily would have seen. Cool. Alyssa left a comment. I assume she is ready again. Okay. Okay. So let's look down that bond. I don't know if you want to turn your camera on for this, Alyssa, just so you
I
can
would
show
love
us the model.
to, just so that I can show you the model and then
Yeah.
just to see what I'm doing wrong, if that's okay.
Yeah, absolutely. Let's do that.
You might see some folks in the background. Okay, I'm ready. So
Okay.
can I just show you the model I made and then
Right, and so it might be what I want to just you're going to look at this. Your camera might be mirrored, so it might confuse people. So let's just take a look at the model you made and let's figure out if you're mirrored or not.
okay. So so this is the one that I made. So here is the C2H5 group.
Yep.
This one. And then
Yep.
this would obviously be the first one. And then the yellow one is the bromine.
Okay, so I think so you're facing the bromine towards you right now, right?
Yes. Yes.
So you're holding the bromine is in the middle, but the CH2, I just want to make sure that you and I are aligned and your camera is making sense with mine.
Mhm.
I'm seeing you hold the ethyl group that's attached, like the ethyl group that's attached to the bromine. Am I sharing my screen? Can you see my screen? No?
I can just see you.
Okay, I'm going to just share my screen. You seem to be like sitting there in dark mode. It's pretty good.
Yeah, I can see you now.
Okay. So I'm looking at you, and so if you keep holding your model up,
Yeah.
the ethyl group you're holding, that's next to the bromine, are you holding that in your right hand or left hand? The other one, the other hand, the other ethyl group. Is that your right or your left hand?
So
It's
it
your
would
right.
be my left hand
Right. Okay.
if I turned it around.
Yeah. Okay. So I'm holding it in my left hand. I'm seeing it in my left hand on the screen.
Okay.
So if you want to grab with your left hand, and now just check. So the bromine is pointing away from you, which is good.
Yep.
Now let's rotate it so the hydrogen points away from you on that other one with your right
This one?
hand. Yeah, point that hydrogen away from you because you want the methyl group to be in the plane of the chain because that's the conformation we've drawn there, right?
Right. Yeah.
Okay, so you should have all the other atoms like that. The ethyl group next to the bromine, the carbon with the bromine on it, and then the methyl and that carbon. All those 5 atoms should be in a plane. Like you should be able to look straight down them and they're all in a plane. Okay, awesome.
Like an M.
Okay,
Yep.
so now you're going to rotate it, the molecule, so you look straight down that bond towards the carbon bromine. Exactly. Yeah, you look like that. Everyone else is looking at it backwards now, but you're looking at it straight on. And what you should be able to do is rotate it such that you're seeing what I'm seeing down here for this back carbon. The bromine is in your right hand, the hydrogen's in your left hand, and the methyl group is kind of coming straight up.
Yep, that's what I see for the back.
Okay, so for the front one, what you should see is the methyl group on the front going straight down.
Yep.
The ethyl group in your right hand.
In my right hand.
Left.
Hand. Yeah.
Left hand. I am not good at left and right. And the hydrogen in your right hand. That's what you see.
Yep. And then a hydrogen coming up. Yeah.
Okay. So if we, okay, so I think you can stop sharing your screen. I think you've made that properly. So we can look at this and you can maybe follow along as we jump around. So actually what I'm going to do, or stop sharing your video. What
Sorry, that's
I'm going to do is I'm going to pull up the, give me a second, I'm just going to pull up the answer key. Not the answer key, but the questions. I think hopefully she sent them to me as a PowerPoint. I don't remember how she sent them to me. I got his Word file. Okay, so I'm just gonna. Okay, so I don't know if, so I'm just going to, okay. Just have it on 2 different pairs. So if I pull this up, what we're looking at with this, I'm just gonna be drawing it down on my screen that I have in front of me, and I'll switch back to that. Okay.
Okay, I see it now.
Okay,
I'm not sure how I messed it up before, but I see it now. It makes sense.
Yeah, so this is what answer A was. And I get that by just rotating the front carbon by 60 degrees and the back carbon by 60 degrees. Right?
Right.
Yeah. And the other ones, if you try and build them, what you'll notice is one of the stereocenters is flipped. It's backwards. I'll have something in my right hand which I need in my left. It's just not the same molecule. Like
Okay.
I've drawn either diastereomers or enantiomers or what B, C, and D is. Even if we didn't cover the actual words for that yet, it's what they are, and it's because their stereocenters are different. Like things aren't in the right spot.
I guess I was just confused, like, when something is coming at you, it should be like overlapping with the back carbon. Like in this case, it was the ethyl group that was coming out at the page, or like, sorry, coming out of the page. Like if you're building a model and then it's supposed to be like right behind the like M chain, right? If that makes sense.
Well, it will come straight towards you, the ethyl group. But
Right.
what you have is like this is, I'm sharing a screen. This is one way to draw this molecule. But I've got lots of other ways I could draw it, right? Like I could have drawn it like, you can rotate things. I've rotated this, so everything's going to flip. That's the same molecule. I've just rotated one of the bonds. So I think there's no, it has to be in this because I think what you're saying is, okay, it has to be in this conformation. No, it doesn't have to be in that conformation. It can be in many conformations. We tend to draw the longest chain as a zigzag for convenience only. It doesn't tell us that's how it sits. It doesn't tell us that that's the most stable conformation for this. It doesn't tell us it's preferred. It's in this case, it's not, because the ethyl group is actually bigger than the methyl group. So this should be in the main chain, not this. It's just for convenience, we draw it one way. But there's no other ways are perfectly fine too. And that's why it's all three-dimensional. Everything can rotate. And yes.
Okay.
Yeah.
Thank you.
I'm not sure how helpful I was. Olivia, then Megan.
Hi, Dr. Trant.
Hey,
I had a question about Newman projections on the assignment as well. Do you want me to share my screen?
Sure, go nuts.
Easier? Okay.
It should slant over mine, I hope.
Okay, can you see it?
Yeah.
Okay. So this was the one that kind of caught me up a little bit. So I also made a model, which I find helps me a lot.
Good, great.
But as you can see, it's easy. Like I don't have trouble determining that A and D are incorrect. But for me, I didn't know, because this is obviously a bit more eclipsed than D, which is staggered. And I think I'm just having trouble determining when you know that a molecule is, staggered as opposed to eclipsed, if that makes sense.
Okay, so how did you have no trouble determining that A and D were incorrect?
Well, because I build out the model because I'm more of a visual person, so it's easier for me to see it that way. So just the way that I I drew out each of the molecules, and then using my model kit, I was able to determine that A and D were wrong. But then in terms of B and C, I was having trouble determining which one was right, because when I was rotating my molecule, I kind of figured out, I thought it was C because you don't want something to be eclipsed. You'd rather it be staggered.
Okay, no, I agree. You're absolutely right. You don't want them to be eclipsed except to be staggered. But okay, so do you see a difference besides one being eclipsed and staggered? Do you see a difference between B and C? Look at the front carbon.
Yeah.
Okay. And walk fluorine to methyl group to hydrogen. So
Oh,
it's
okay.
clockwise on B and it's counterclockwise on C.
Gotcha.
And on the product, it's clockwise.
Oh, okay.
So that's why, because C and B are not the same molecule. And yeah, stagger's not great. I agree with you. And I think if I, you know what, I wouldn't, it would be a typical test bank question if I had said which of these was a better representation. One was staggered and one wasn't. They were exactly the same molecule and you had to pick the staggered one. That's evil. This is only moderately evil because one of them is the wrong molecule.
Okay. I just didn't see that, so thank you for pointing
that out. That's it. I think just like for this, what you should be thinking about with these questions like this is you're trying to focus in on what are the differences. Whenever you have a multiple choice question, always focus on what are the differences and identify what they are. And I think you missed the stereocenters are probably the most important thing. You did identify a difference between staggered and eclipsed, and maybe a bit of a red herring difference, though didn't really put that much thought into it. I think it was just this is just the angles that she drew when she wrote the question. Yeah, okay.
Okay, thank you for your help.
Great. Glad we sorted that one out. So Megan. If you're still wanting to go, Megan, you're muted right now. You're unmuted, but I don't hear you.
Their messages are in the chat.
Ah, that is useful. Okay, your mic isn't working. Yeah, I'm throwing this question out. So the reason I'm throwing this question out is it's right, but and if what you did, Megan, is you said, I think C is going to be stabilized by resonance, so D is going to be D is going to be the worst. That's exactly the logic I want you to be doing, and it's a minor detail on where the proton is and the orbital it's in, because the negative charge is in a p orbital versus an sp3 orbital for O, and a p is further away than an sp3, so it's better to be in an sp3 than a p. It relates to what we were discussing, but it's also contradicted to what we've kind of said, where hey, resonance is always better. So I'm tossing this question because I thought we had done C slightly differently. So if that's what you did, that's why I'm throwing this out. And I'm going to throw out the equivalent question if you got any of the other questions for this one. We're just going to give everyone a bonus mark. Because if you thought, oh, you thought it was A, well, A would actually be very stable. A would be very stable because you got resonance both ways. And so strongest base is the least stable charge, the one most likely to react. Okay, so you're going to benefit from getting a bonus mark because you didn't answer it wrong. I would have accepted D or C. So yeah. I'm going to try and figure that out, Alyssa. Maybe. I need to do some thinking on to how to actually go through and sort that out. It was a poorly phrased question. Okay, Parveen.
Hi, I had a question about number 4D, sorry, no. Yeah, 4D on assignment 0.
I will pull it up. It's assignment X, right?
Yes.
Yeah. Knowing my numbering, I would have an assignment 0. Because I just kept inserting new ones. Okay, 4D. So what we have is we have a, I'm just going to share my screen so everyone can see it. And then you can tell me this one, right?
D, the last one.
E?
Or D, no, second last.
This one, right?
So yes, this one.
Okay.
So I thought that the answer would be on the right side because I thought the chlorine is larger in size compared to the fluorine. So that's why it would pull harder. But your rationale said the fluorine pulls harder.
Okay. So, so let's talk about actual localization of charge on an atom versus inductive effect. So when we were talking about charge, and you're right, let's say the negative charge was directly on chlorine or fluorine, and those were our choices.
Mm-hmm.
The chlorine would be more stable because it's larger. Cl minus is more stable than F minus. You're absolutely right. Okay. Do we have a Cl minus or an F minus here? Do we actually? Yeah. What we're doing here is we're not trying to stabilize the full charge on the atom, which is where that comes in. What we're trying to do is we're trying to pull density out of things through bonds. So instead of like localizing all the charge on the atom, what we're doing is how strong does it pull? I think it's like I'm trying to think of an analogy. Like there's different types of strength. So let's say you have, I'm going to be completely sexist here. Let's say you have two men. One is, you know, incredibly strong but kind of skinny, and the other one's really, really broad-shouldered. And let's say we have a goat. Now, the broad-shouldered man can probably better carry the goat. If the guy has to carry the goat around, I want the broad-shouldered guy. But if I need to pull the goat, I probably want the stronger guy. And the goat being the charge. So with the fluorine, we're trying to pull electrons through bonds. And fluorine pulls harder because it's more electronegative. It polarizes that carbon-fluorine bond greater. So the carbon adjacent to the fluorine is more positive than a carbon adjacent to a chlorine. And then that propagates down the chain to get a more positive site next to that O minus. Whereas if the charge was entirely on the atom, then the size would matter.
Okay.
So
Okay, that
induction
makes
is
sense.
really driven by electronegativity because we're pulling through bonds. We're not trying to balance the entire extra charge on our own. Whereas in those examples where you have a Cl minus and an F minus, you almost, in those cases with the halides like that, you never have resonance. So it's bearing the entire charge on its own. And it's not an inductive effect we're looking at there. It's a, how well can it hold the extra electron?
Okay. Okay, thank you so much.
Yeah, no, it's just competing things. Chitra.
Hi, Dr. Tran.
Hey, Chitra. How you doing?
Good, how are you?
Awesome. What's up?
I just had a question from the live lecture on October 6th. The last example that we went through, converting the double Newman to a chair configuration, the one where we had to flip it.
Yeah.
I was hoping you could go over that, and particularly how we know that we need to kind of flip the Newman to look at it from the other side.
Ah.
Chair configuration.
Okay, I'm going to. That's a good question. So let's draw 2 chairs. These are the chairs we tend to draw, right? You don't need to if you can do this differently. So the first thing is I do it because it's the way my brain works. I'm not saying this is the way your brain has to work. If your brain can see something different, it can. So what I'm going to point out here is if I'm thinking double Newman with either of these, I'm looking down these 2 bonds on both of these chairs. That's how my brain works.
I don't think you're sharing your screen.
Oh, shit. Well, that's going to make it difficult. It's a very polite way to say you're not sharing your screen. Okay, so let's say we draw the 2 chairs that we can. We generally draw. When I think a double Newman I'm looking down either of those 2 sets of bonds. That's just the way my brain works. But, you know, you don't necessarily need to be doing that. If you can, and that's because I can kind of picture myself looking down them from my vantage point. It doesn't necessarily need to be that way. If to you you're thinking that those are not how I would look at this, I would pretend that my eye is over here, and I would be looking down these 2 bonds. Or I pretend my eye is over here, and I'm looking down these 2 bonds. Like if that's how you see it and you sort of picture yourself on the left-hand side, that's great. I don't. I kind of picture I'm looking straight onto the page, and for me, the easiest ones to look down are these 2 because they're kind of roughly it's easy for me to envision looking down them from my viewpoint where, you know, I'm kind of down here or a little bit over here. So problem here and what I want to highlight is if we do this, and I look at it this way, front, back, back. And like it's just because that's the way perspective works. So if I have a double Newman projection, and there's just stuff. I don't know. The problem we got here is that if we're looking at this, this is the front, and that's the back. Now, on the front here, this carbon of the cyclohexane chair is down below the plane. My axials on these 2 carbons are up. The problem is my axials on these 2 carbons here are all down. I can't draw this as that. I can't like unfold it onto these chairs. Now I can unfold it just fine onto these chairs because if I'm looking there, my 2 axials are up. Right, it would be CH3 fluoride, or here CH3 fluoride. That's fine. So if you can see the chair that way, go ahead, be my guest. It's completely correct to do it that way. I have trouble visualizing that because then I have to rotate my entire head and my Newman projection, everything else. So to unfold it using these 2 common chair conformations that we draw, where the front carbon between the 2 guys is up. So that makes these axials down at these positions. There's no way around that. If I'm using these projections, that's not what I've got here. So what I can do is I can either rotate this around sort of a middle axis 180 degrees, or I can flip it. I can flip it any way I want, or I can flip it upside down, like literally like freaking pancake. It's like this, and now it's like this. Like that's fine too. So then my red carbon would be on the right, my blue carbon, and everything's just upside down. I don't. And that's fine. I just flipped everything upside down. And that's okay because I'm not rotating, I'm just, moving a static molecule around, and you can do that. And now I have the situation which I want, which is my axials on my front carbons are down, which is the view I have, and this middle CH2 is above those two, which is the view I have. So that's why I had to rotate the Newman projection, because I accidentally drew it in a way that I couldn't unfold it onto the chairs I'm used to working with. Did that make sense?
Yeah, I see. That makes sense.
Yeah.
So, and in this example, you flipped it like upside down, but then the one in the lecture, we flipped it or right to left, I think.
Yeah, I instead of going upside down, I went like that. I rotated in like along the middle axis. So I rotated my hand backwards. So I just kind of looked at it from the other angle, from behind.
Okay.
And either one's completely correct. I'm just rotating a molecule. There are infinite number of rotations you can make to any molecule.
Okay, so as long as you can get the substituents to align with how you want your axial positions to be in your chair configuration, it's fine.
Yeah. As long as you
I'm
unfold it
flipping it.
properly. You could go directly
Okay.
from this to this. That's fine too. Same answer.
Mhm.
But I have trouble seeing that. I think that's harder. But if you don't have trouble seeing that, go nuts.
Okay, I see.
Mhm.
No, I think it's easier to visualize it looking at the two on the side, the way you look at it.
Yeah, I think so too.
Okay, so in these cases, when you're looking down those two bonds and then your substituents don't match up from your Newman's diagram to your chair configuration, you can flip it either upside down or left to right or right to left, whichever way. And
Yeah.
as long as they fit, you can just then kind of translate that.
Yeah. Like if I'm sketching this guy out based on this guy here, what I'm going to see on my left-hand side, I've got an axial fluorine down. I've got an iodine equatorial on the back carbon, sort of in a down position. There's an axial up hydrogen. There's an equatorial hydrogen. I'm just going to delete the circles. Now on this carbon, we've got an axial up methyl group on the back, and then everything else is a hydrogen, so I don't need to draw them in. But kind of jumps out at you as being a way to do that. My fluorine's not very axial. I'm going to make it a bit more axial. There. That answer the question, Chitra?
Yeah, that's good. Thank you so much.
Okay. Hey, Dea.
Hello, can you hear me?
Yeah.
So I was looking through one of your assignments. I think this was assignment 1, and one of your questions had cyclopentanes and draw the most stable conformation.
Yeah. I'm not going to ask you that.
Oh, okay. Because I skimmed the answers, they kind of made sense. You just put one thing on the tip of the envelope and then one thing at the other side.
Yeah.
Okay.
The tip of the envelope gives you like extra axial and extra equatorial kind of positions.
Mm-hmm.
Like the equatorial is like super equatorial. And it's by far the best place to put the big thing. And so that's why that goes super equatorial. Always the biggest thing goes super equatorial. But I'm not going to ask you to draw 5-member ring conformations. It's just, this is one of those things where if you really understand this and think about it, it might make sense to you.
Yeah, okay. It made sense to me. I just want to make sure if we were responsible for that on the
No,
test
you're not
or
going to be
not.
responsible for that on evaluations. I'm not going to.
Okay. And I have another follow-up
Later
question.
courses might make you responsible for it and assume that you're aware of it.
Mm-hmm. Oh, okay.
Yes.
And another follow-up question, just quickly. 'Cause I'm assuming you're going to ask us on the midterm, rank the following based on acidic strength. So how would you, what would you want specifically? Would you want us to validate each step? So for this assignment, you had a rank formic acid, not formic acid, methanic acid, and then ethaniol and stuff like that. So would you want us to rank them step by step?
I think if I would, so the exam is not going to be multiple choice, so I probably would not ask you that question.
Oh, I just assumed you list 6 random ones and then say rank them based on, or would that be not a fair question?
Yeah, I could give you 6. Well, no, it'll be a fair question. I could give that to you, and I could say justify your choice. And so you would have to sort of rank each one next to its nearest partner and sort of say, this is why I'm choosing this one over that one. And then there would be part marks for stuff, right? I hate multiple choice for real evaluations because you being able to justify your answer is the entire idea. So even if you're, I think we saw an example earlier where I was like, okay, we've got this SP3 versus, you might not have been here for that. It was O- versus equilibrium 1, or so they can do resonance, and it came down to, in reality, it comes down to the hybridization of the electrons. We just haven't discussed it in that much detail, and I keep focusing on how important resonance is. And so reality is true, and that matters. It was a poorly phrased question. I'm throwing it out. But I would have accepted either answer saying, okay, well, this one's more acidic because of, the argument over the orbital state, or this one's more acidic because of an argument over resonance. And because you can justify your answer, we have a lot more flexibility in saying, yes, you understand why you're putting this rank the way it is.
Okay.
So if I did that, it would be maybe a form, let's say I gave you 6 and I made it a 5-mark question. There would be 1 mark for getting the rank right and 4 marks for justifying each pair, why your order is what it is.
Okay, I see. I think that's it.
Okay. This afternoon, I hope to be posting at absolute latest. It will be tomorrow morning, but I think it's gonna be this afternoon. I'm gonna post some old midterms, so people can take a look at that. You'll note they're a lot like the assignment questions. They really, really are. And actually, in the past, I've drawn midterms, used a couple of assignment questions on each midterm. I'm not doing that this year for obvious reasons because it's open book. But they're typical. I would say the assignment questions are harder than midterm questions generally.
Are you talking about your Trant assignments?
Yeah. Those assignments are harder than a midterm, but they're in the same style. Because normally with those assignments, I'm trying to get you to work at something and then teach you something. Because they're not, I give you a million questions and say, here's a slightly different structure with exactly the same principle over and over and over and over and over again. And that's busy work. Once you've learned something, you've learned it. You don't need a ton of busy work. What you need to be doing is seeing slightly different iterations of things and how things are balanced differently and trying to use them as a teaching tool. So that's why the assignments are what they are. But there's often tricks on there which are kind of cruel. I don't feel guilty about them on an unmarked assignment because it's oh, okay, I see that. I get that why that is. But on an evaluation, a cruel new trick is a cruel trick, and that's not good. Yeah. So the assignments are harder. But if the way you do your and I'm sure you guys are showing up to an office hour, so this doesn't apply to you. But if the way you do the assignments is you you know, you flip to the answer key and you check the answer key and you go, yeah, I get it. That's not as, you're not getting the full value of the learning experience out of it, because the idea is to try and work through it and then sort of catch up where if you're wrong, why you're wrong, where your logic fell apart. I'll take, I guess, one last one. So Melitza, you're.
Okay, I was just wondering why water would trump an acidity versus a
Alcohol?
no, it was
Oh, good.
a ketone, like it was a three-chain carbon with a ketone at the number 2.
It was acetone. I think that's the question.
So is why is water was it this?
Yeah, it wasn't in an equation. It was just in the ranking acid in decreasing order, and
Okay.
the H.
So the reason why is acetone. This is sitting in a p orbital. This is sitting in an sp3 orbital. This is further out. This is closer in a bit more. So it's kind of like the sp thing we were talking about. Acetone does have resonance, but it doesn't compensate, and that's why I'm not super happy with the question. I think that question, though, there was something else wrong with the other answers, because it was there was always something else drastically wrong with the other answers. So I don't think your answer came down to this differentiation.
Yeah, I was just wondering for me,
Yeah.
I just wanted to know like on an exam because I was following the rules and I said, oh, this one has more resonance, so like I'm not gonna
Right.
even look at hybridization.
And my pen is currently stuck for some reason. Oh, there we go. Keep, yeah. Yeah, so again, hybridization was higher rank than resonance as importance. Like it's right up there with the atom as really being important. If there's a lot of resonance, it overcomes it, but there's only a little bit of resonance here. And what we're really looking at is this is by far the more stable resonance structure of these two, because you have a negative on an oxygen, right?
Yeah.
You're not like, yeah, it does resonate onto the carbon, but that kind of sucks. So yes, if there's no resonance, and again, this is in a p orbital. If there's no resonance and the electrons are in a p orbital, sure, this wins. But having an sp3 is better. Just like as we were saying, having an sp is better because you're closer to the nucleus, so that wins. I don't like this, like on an exam, I'm not going to make a question that's kind of like this. I think it doesn't get to teaching a fundamental concept there. You're weighing apples and oranges. And I know the difference between an apple and an orange. You guys have less experience with that. It's just, it's not asking something fundamental. So I'm not going to ask you an exam question like that. And I think that question did come down to something else that was horribly wrong in one of them.
Okay, and then you mentioned does hybridization trump resonance? Because I think we have it that resonance is second and then hybridization is third.
It depends on the amount of resonance present. Like, yes, in this case, this guy's more acidic, but in this case, then we have two of these. This guy is more stable. Or so we added one extra resonance structure. Under this hybridization trumps. Under this one, the resonance would trump that. There, all these I can give you sort of a general rule of thumb. So generally, the way I will ask questions, resonance is going to be more important because it's the way I think, and it's kind of questions I'm asking. And almost all the questions I have that come down to resonance, there's more than one resonance form. There's like lots of resonance forms. So you really do localize in a charge because I like questions like that. The other thing is I get more unique questions. If there's only one resonance form, that question exists because you just have limited space to do it. If I added like a few, suddenly I'm generating molecules that nobody's ever drawn before very easily. So in general, resonance is more important because normally you're going to have more in this class because normally you're going to have more resonance structures. On a case by, but it is on a case by case basis, so it really depends how much resonance.
Okay.
I'm sorry.
It's okay.
I really wish it was like cut and dried and I could say this always, that's why they're trends and rules of thumb. So when I say something is always true, I mean always true. I didn't say this was always true. I said this is kind of a rule of thumb. And it is.
Okay. For like an exam, would you have us like, I guess, like weigh out hybridization versus resonance?
No, I'll probably have you for an exam. I'm looking to test your knowledge. And so I'll have you weigh out like with like. So I normally would have you weigh out hybridization versus hybridization or resonance versus resonance.
Okay.
Like resonance and induction can also flip places if the induction is really strong. But I want you guys to be focusing on resonance because I want you thinking about it because it's really important for lots of other things, even if I'm outsizing its role on charge stability here on the acid-base stuff, and I am, by putting in like molecules with just fuck tons of resonance, it's really important to be thinking about resonance because that determines a lot of reactivity. So I'm trying to get like an excuse to do more resonance earlier in the course because it's really important to see it lots and practice a lot. Yeah. Okay. Unless they're really sharp, Chitra and Alyssa, I'm going to call it because they're really short. I'll let you guys.
Yeah, it's just a really quick question. So when you say like SP3, it's more stable. So the higher level of like SP3, SP2, whatever, the higher level that those are in, like the electron pairs or whatever, like the molecule combined, does that make it more stable?
Well, an sp3 orbital is lower in energy than a p orbital. An sp orbital is lower in energy than an sp3, right?
Yes.
Right. And it's lower in energy because those electrons are closer to the nucleus.
So SP is a lower energy than SP3.
Absolutely.
And then SP2 is a lower or a higher energy than SP?
Yep, but lower than sp3.
Okay. Okay.
And p is higher than all of them.
Okay. Thank you.
S is lower than all of them.
So
and
when you say, sorry, go ahead.
Go on.
When you say p orbital, do you just mean like making a double bond or?
Yeah, like the electrons are drawn the other one there on the right hand side. That's in a, that negative charge is in a p orbital.
Okay.
Because it's involved in double bond making.
Okay. Got it. Thank you.
It's got to be in a p orbital. Yeah, so it's higher energy. Chitra, or do you still have your hand up from earlier?
Oh no, I'm sorry, I don't have my hand up. I'm good.
Okay. I think. Lisa, did you put your hand back up? Oh, Madison has her. Oh, okay. You know what? Sure.
I just put a few questions in the chat while people were talking.
Oh, okay. Yeah, I'm going to double check, Madison, if that's true. You're not going to need to name molecules on a midterm, no. Okay, I've just got a phone call coming I'm going to take, and because I scheduled at 10 o'clock, so I will catch you guys later. Is that okay? Good luck. I'm just going to leave.
you.
Bye.